Welcome back to Chapter 4. In Section 5, we'll be switching from linear equations to linear inequalities. A system of linear inequalities is made up of two or more linear inequalities. An ordered pair is a solution to a system of linear inequalities if it is a solution to each linear inequality in the system. To find the solution set, we will first graph each linear inequality in the system, and we'll do that separately. Then, if the solutions to the individual inequalities intersect, then the region of intersection is the solution set to the system of inequalities. Let's take a look at an example. In this example, we have two linear inequalities. We will first graph both of them and see if they intersect. Let's start with the first one. Y is greater than x minus 6. In order to graph this inequality, let's first take a look at the line y equals x minus 6. This is the line with y-intercept negative 6 and slope positive 1. So we can plot the point 0, negative 6 and use the slope of 1 to plot some more points. Since this inequality is a strict inequality, we only want a dashed line here. This means that points that are on the line are not part of the solution set, just one side or the other. Now let's test a point to see which side is the solution set. Let's test the point 0, 0. When we substitute 0, 0 into the inequality, we have 0 is greater than 0 minus 6, or 0 is greater than negative 6. This is a true statement, so the point 0, 0 is in the solution set for this inequality. We will shade the side that 0, 0 is on. Now we'll switch to graphing the second inequality. 2x plus y is less than or equal to negative 1. First, we'll focus in on the actual line, 2x plus y equals 1. Subtracting 2x from both sides, we have y is equal to negative 2x minus 1. This tells us that our line has a y-intercept of negative 1 and a slope of negative 2. And that's enough information to begin plotting some points and graphing our line. Notice at this time, we don't have a strict inequality. We have a less than or equal to. So we want a solid line for this graph. Now let's test a point. We can test the point 0, 0 because it's not on the line, but let's choose a point that's a little more obvious. Let's try 1, 1. When we substitute 1 for x and 1 for y, we have 2 times 1 plus 1 is less than or equal to negative 1. Or 2 plus 1 is less than or equal to negative 1. That's 3 is less than or equal to negative 1. This is, of course, a false statement, so the point 1, 1 is not in the solution set. We need to shade the other side of the line for the solution set. Now that we've graphed each of the linear inequalities separately, we need to figure out where they intersect. As far as the shaded regions go, they intersect here. But we still need to take care of the border. Notice that values that are on this line are in both solution sets, but no values that are on the dashed line are in the first solution set. So when we draw this border, we need to make sure it's a dashed line. So the ordered pairs that are solutions to this system are in the dark shaded region and on the dark line. Let's do another example. In this example, we once again have two linear inequalities, and we will start by graphing them separately. First, we'll look at y is less than or equal to 2x minus 3. We'll begin by looking at the line y equals 2x minus 3. This is the line with y-intercept negative 3 and slope positive 2. We can plot the y-intercept and then use the slope to plot some more points. Since we have a less than or equal to symbol in this inequality, we want to graph this with a solid line. Points that are on the line are part of the solution set. Next, we'll test a point to see which side of the line the solution set is. Let's test the point 0, 0. When we substitute 0 for x and y, we have 0 is less than or equal to 2 times 0 minus 3. That becomes 0 is less than or equal to negative 3, which is not a true statement. This is false, so that means the point 0, 0 is on the wrong side of the line. We need to shade the other side of the line. Now let's look at the second inequality. Y is greater than negative 2. We'll start by focusing on the line y equals negative 2. This is the horizontal line with y-intercept of -2. Since we have a strict inequality, we want to make sure we graph a dashed line. And now we'll test a point. Let's again test the point 0, 0. But if you think about it, we want y values that are greater than -2. So maybe you have some intuition about what the results might be. Substituting 0 for y, we have 0 is greater than -2. That's a true statement, so the point 0, 0 is in the solution set. We need to shade above the line. Where these two solution sets overlap is the solution set for the system. That will of course include where the shaded regions overlap, as well as what is on the solid blue line here, but not on the dashed line there. Now we've graphed this system of linear inequalities. Let's take a look at one more example. Notice that in this example, we have 3 linear inequalities instead of 2, but the process remains exactly the same. We'll look at each inequality separately, just like we did before. If we look at the line that's associated with this first inequality, we have x minus 4y equals 8. Solving this equation for y, we can subtract x from both sides and divide everything by -4. This gives us the line y equals 1/4 x minus 2. This line has a y-intercept of -2 and a slope of 1/4, a rise of 1 and a run of 4. Since this is a strict inequality, we want a dashed line. Now let's test the point 0, 0. Substituting 0 for x and for y into the inequality, we have 0 minus 4 times 0 is less than 8. That becomes 0 is less than 8, which is a true statement. So we want to shade above the line. Now let's look at our second inequality. We have x is greater than or equal to 1. The line that's associated with this inequality is the line x equals 1. That's a vertical line with a y-intercept of +1. And since we have a greater than or equal to symbol, we want a solid line. If we again test the point 0, 0, we have 0 is greater than or equal to 1. This is not a true statement, so we want to shade the other side of the line. Now let's take a look at our final inequality. We have y is less than or equal to 3. This is associated with the line y equals 3, which is the horizontal line with y-intercept of 3. Since we have a less than or equal to symbol, we again want a solid line. Testing 0, 0 once again, we have 0 is less than or equal to 3. That's a true statement, so we want to shade below the line. Now, can you see where these 3 regions intersect? They intersect precisely in this middle portion right here. And that's the solution to this system of 3 linear inequalities. And that will conclude Chapter 4, Section 5, where we graphed systems of 2 and 3 linear inequalities.